Okay, we're going to break ozone now. And I want to remind you that we are in the outer atmosphere where there's plenty of oxygen all over the place. See, oxygen, oxygen, oxygen. These are oxygen gas, O2, 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 O2. And there's plenty of ozone around. Ozone like this. And I want to introduce a new ingredient, but first I guess I want to remind you if you have ozone and whoops, I decapitated one, and a single free radical oxygen happened to come around, all three of these are not that happy because nobody's getting the attention they deserve. So this guy comes around, any of them would rather go to make oxygen gas, leaving oxygen gas, everybody wins. It could be this guy leaving, everybody wins. You can see it's on the screen there. Every time, ozone plus a free radical would make oxygen gas and a combination there. And that's the strongest possible bond, and they're not that picky. So I want to remind you of this thing about desperation and clinginess. We've got oxygen, we've got ozone, and we're ready to break up the ozone layer by introducing a loose Hofbrinkel atom. The one I'm going to use is the most common one. Oops, sorry. The one I'm going to use is the most common one, chlorofluorocarbon 3. Oh, I forgot to make the little, I forgot to make the little subscripts. That's okay, you can deal with that. So there's chlorofluorocarbon, Cl3Fc, chlorofluorocarbon. And in the presence of ultraviolet light, one of those can be broken off, right? Because ultraviolet C can break anything. So I want to introduce a particular and unique Lego character. Notice I gave this guy a wacky hat. I gave him a wacky hat so that you'd be able to keep track of this guy because he's going to do a lot of damage. Okay. This is a Cl asterisk. That's a single chlorine atom. He has a wacky hat. That's this one right there. So you could have had like a really complicated molecule, and in ultraviolet C, boom, a single chlorine atom. And you have to know that that's a single chlorine atom. And now things are going to get interesting. Okay. Remember, these guys are in this awkward threesome. Beats being alone. But nobody's really happy because they're not getting the attention they deserve. And this guy happens to come around. Now, any of these would be happy to leave. So let's say this guy leaves. And they make a relationship called ClO. The remainder is oxygen 2. They're happy. But that ClO, they're like, hey, all right, at least we're not single. But in the outer atmosphere, there are occasionally, remember we talked about single oxygens. And if a single oxygen comes around ClO, this oxygen's like, hey, thanks, chlorine, but I'm actually a secret racist. I would rather be with my own kind. And that single oxygen plus the other single oxygen make the strongest possible relationship, leaving this guy single again to go out and do it again. Boom. But that relationship's not so strong. This guy's a racist, so he says, nah, I'd rather be with my own kind. And that leaves chlorine, single, ready to go wreck another home Oxygen gas is always happiest alone, and oxygen's always happiest with another oxygen. And so what you can't quite see is that on my desk, this guy tore up all my ozones and he's still single. In other words, a single chlorine atom can destroy the entire ozone layer because they're desperate and they're clingy, but it's also interesting to point out that they're a little bit racist. Chlorine can take a single oxygen away from ozone. That's what destroys the ozone layer. But remember that this is all a way to talk about preferential bonding and electron geometry and stuff. Chlorine plus oxygen is not quite perfect because if there's another single oxygen around, they're going to leave chlorine single again. There's a lot of ways to draw this. Remember, we're in the outer atmosphere, so there's plenty of oxygen, there's a lot of ozone, there's a lot of radiation around, and a single chlorine will split all the threesomes, but never hold on to that extra oxygen for very long. It's on the screen. The chlorine loses, the chlorofluorocarbon loses the single chlorine, and now that chlorine, anytime that it encounters ozone, will take one of the oxygens. That's an easy reaction because these guys are happy and at least they're not alone. But that's not very strong. Oxygen prefers other oxygen. So when these encounter a free radical oxygen, it'll make more happy oxygen. In other words, this is like a home wrecker that goes through the ozone layer, essentially transforming all the ozone back to plain old oxygen. It's like a temporary let me get you out of the threesome until you can find the right match relationship. Unless, of course, a single chlorine happened to bump into another single chlorine and then they could get together. That would be the end of ozone depletion. If we wait long enough, ozone depletion will eventually stop because chlorine atoms will eventually find other chlorine atoms. But that can take a long time. A single chlorine atom can last in the atmosphere for 1 to 12,000 years. So it's kind of sketchy when there's a lot of chlorine up there. Here's that drawing again. Ultraviolet breaks off a chlorine. That single chlorine cannot be alone. Hofbrinkel, that gets an asterisk. That's a desperate, clingy single, Hofbrinkel. So that chlorine will steal an oxygen away from ozone. Chlorine oxide is not very strong. Oxygen gas is happy. Chlorine oxide is not very strong. So when another oxygen comes by, they're going to make a relationship that lasts longer, so to speak. So ozone depleting chemicals are anything which can split off one chlorine or one bromine. Technically one fluorine would work, one iodine would work, but those are just not really common out in the atmosphere, in the outer atmosphere. So ozone depleting substances, you should have a list from the beginning of our unit. Ozone depleting substances were on question number single digits, something in assignment 8.1. And since you already made that list, I won't force it now, or you could copy it again off this screen, that's fine. But ozone depleters are any chemical compound that can get to the outer atmosphere. A lot of these are too heavy, they're held by gravity. So the ones that tend to be hyper enough to get out there are mostly chlorine and bromine compounds. You'll notice that there might be fluorines attached, carbons, other stuff, but the ones that are the most dangerous are the chlorine and the bromine. So these don't usually play as much of a role in ozone depletion. And I'd like you to write down a couple, just a couple. The most common are chlorofluorocarbons, Cl3FC and Cl 2F2C, whatever. Chlorofluorocarbons. Those are the most common, man-made. And then I want you to write down another one, methyl bromide, which is important to remember because it's both natural and used by humans. The only other thing I've ever seen on the AP test was halons. So maybe you would need to know that, but it hasn't come up a lot. I do need you to know chlorofluorocarbons and methyl bromide. You should know the sources. There's a lot of weird chemistry that makes chlorofluorocarbons. Oh man, I lost a slide, bummer. The main sources of chlorofluorocarbon are aerosols, like spray propellants, like spray paint. So chlorofluorocarbons like push the paint out because you can pressurize them. So aerosols, styrofoam, and coolants. So you should know that. Aerosol, styrofoam, coolant. There's other sources, but those are the easiest ones to remember. And for methyl bromide, you should know that it's first of all naturally occurring. And also humans add it in agriculture, especially in Santa Barbara County. I believe we're the world's largest emitter of methyl bromide. Important now because that bromine can split off ozone. I like this diagram because it shows you in the presence of sunlight, oxygen can become ozone, right? Ozone is always being built on its own. It's a naturally occurring process. So there it is being made on its own. But sunlight can also split off a chlorine from chlorofluorocarbons, and that chlorine can destroy ozone, making more oxygen gas. So it's like a two-way street. If we make too much pollution, we'll run out of ozone. If we kick back on the pollution, sunlight will eventually make more ozone. Got it? Ozone's being made naturally. We add ingredients that destroy it. Almost done. Now here's what's interesting. When we noticed that the ozone hole was shrinking, we passed regulations to limit the production of ozone depleting gases, and it worked. Remember that these gases last for a long time in the atmosphere, so we stopped making them, and after a while they stopped eating up ozone, and ozone started to recover. Look down here, that's ozone recovering. But recently, that red line shows you that recently ozone depletion has started again. We're losing ozone again. Because what's interesting is in some parts of the world that weren't invited to the meeting, they didn't sign the deal. There's a lot of countries that we didn't really think would be a big whoop. Like, who would have thought Nigeria would be a world leader in production? Or Brazil, or at the time Indonesia, even India I don't think was invited. The meeting that regulated ozone depleting substances was like a, what do you call it? Like a skull and crossbones meeting at the international level. So it was like the United States, Canada, European Union nations, and a few others. And that really was the majority of the world's business planet in the 1980s. So all the big manufacturers of ozone depleting substances, they all got together, they had a meeting, and they said, okay, we're going to stop because this is scary. But they didn't even think to invite the little guys. And a lot of those little guys in 2020 have pretty big happening economies. So check this out. Ozone depletion has skyrocketed. The total amount of ozone over the South Pole got to its lowest ever in like 2015 and 16, because we had to go back and make a second meeting and be like, oh yeah, sorry bro, I didn't invite you to the party, but maybe you shouldn't make ozone depleting substances because they're going to kill us, and we'll include you in some trade deals. A lot of those international trade deals come with conditions. So like a lot of people don't like international trade. no opinion at this moment. But when you like start a relationship to let Indonesia import t-shirts to the United States, you can say, just saying, you have to not make ozone depleting substances. So that's why ozone is starting to recover again. We predict that ozone around the world will be back to normal levels in the year 2100 or so. These chlorines will eventually find another chlorine. Gravity will pull a lot of the other heavy stuff back down, and natural oxygen formation to ozone will allow the ozone hole to recover. Finally, I found you another image that I thought I would throw in a previous slideshow. It was a little bit confusing. I think this one is a little bit better. Ultraviolet C is immediately blocked by any concentration of atmospheric gases. Ultraviolet B is starkly reduced by the ozone layer, and ultraviolet A makes it full bore down to the planet and technically a little bit into the planet. Okay. I think I can stop. And I hope you have questions, because I know that's a lot of chemistry and you're not supposed to be an expert at chemistry, but you need to know these. So come see me in class.